So in the last lesson, we introduced you to the linear recurrence relations, which are relations or expressions of this type here, un plus 1 equals a un plus b, with your a and b being fixed values. We're going to look in a bit more depth at this type of sequence, and in order to do this, we're going to consider changing the different values of a and b. So doing this numerically on your calculator. So you'd be asked to work out the first 6 values of these two sequences that we've got here. So if we look at this first example, we've got un plus 1 equals 2, un plus 3, and u naught is the initial value equal to 4. That would produce a sequence of values that look like this. u1 would be 11, u2 25, u3 would be 53. Remember that to generate this sequence on the calculator, all you need to do is put in that initial value of 4. You then want to be continually multiplying by the 2, so we would times by 2, and then we're also adding on 3. That's the things that the term, your a and your b terms, that are continually repeating, and then thereafter you just keep pressing equals, and it does generate the sequence of, you've got there 11, 25, 53. If you keep going, u4 109, u5 221, and so on. So what we should be noticing here in this particular sequence is that as we get more and higher term number, the value of that term is also getting bigger and bigger, and it's almost like it's doubling up. And in this particular case, we see the terms are divergent. If we were to plot on a graph what that looked like, so basically it means that you've got along the bottom here the term number and then the term value, and we know that it's rising pretty rapidly, and that's actually that graph is an example showing something called exponential growth, and you will meet these exponential graphs in a later topic. We examine that in a bit more detail. So the second example, recurrence relation, un plus 1 equals 0.5, un plus 3 with the same starting value. So pretty much looks quite similar, however it's the number multiplying the un that's different. This time your sequence looks like this, so it's still going up 5, 5.5, 5.75, but going up at much more slower rate and so on. So 5.875, 5.9375, etc. This time, so as I've said, the values of the term are getting bigger by a smaller and smaller amount each time, and actually if you keep pressing the equals value on your calculator, you will see eventually that what happens is it goes to a value where it doesn't continue to change, so it arrives at the value of 6. Right, we see that the sequence is convergent to a value of 6, and that value is known as the limit. And what happens with your graph in this case is that it levels out, so it reaches this limit value and it doesn't get any bigger, whereas the one on the left, that type of sequence, it was getting bigger and bigger all the time. So if we were to look at some additional values, then, or additional recurrence relations, changing things like the number in front of the un and also the number on the end on also the initial value doesn't make any difference. So this is just some examples that we're going to look at and see whether or not the sequence diverges. So this one here, un plus 1 equals 2, un plus 4, then we're looking to see what kind of sequence that generates. So the difference here is that instead of having plus 3, we've got, like we had in example 1, we've now got plus 4. The sequence that generates does this as well. So it goes up and up and up. And so we would say that sequence diverges. This next one, right, is quite similar to the one that we just looked at, right, but again, the number in front of the UN isn't 0.5 this time, it's 0.2. We've got that added on 4, and the sequence that that produces, and you can check this on your calculator, you get this sequence. This is the first sequence of 6 numbers, and we can see if you keep pressing your equals and your equals beyond this 6 numbers, eventually what happens is it converges to a limit of 5. Example 3 here. What happens with this, the sequence that gets produced with this one, and notice this is a -2 that we've got here, and the values, they are getting bigger, but sometimes it's positive, sometimes it's negative, but both of them are getting bigger. So what we see is it's diverging with alternating positive and negative terms. The next sequence, like this one here, again, it's got a negative value, but it's negative 0.2. And what happens with this one is that, again, if you keep pressing equals, 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 it converges to a limit. Your calculator will possibly end up at 10/3. That's the same thing as 3 1/3, or you might only get it as far as 3.333 with all the 3's. So, but it does arrive at a limit value. This next sequence, right, it produces this sequence 44, 12.8, so it's gradually coming down, but again, right, it converges eventually to a limit. So what we should be seeing at this one here, right, was pretty similar. If we look back up, what was different about sequence 5 to sequence 2 was the same recurrence relation, but we had a different starting value. And in this sequence, right, that didn't make any difference. We still arrived at the same limit value. For sequence 6, this one here, you can check this on your calculator, right, you get these values, -1.8, -5, so on. It's getting gradually, just eventually does converge to a limit of -8.33. So just noticed I missed out a negative sign here, so put that in. So -8 1/3 or -25/3 might come up in your calculator. So what do we notice? What's different about all those sequences? When will it converge? When will it not? So what you should do, and go back and look at the examples, you'll see that the ones where there was a limit value or where they converged, the number in front of the UN was either in between 0 and -1, so it was a decimal value of something like 0.2, or it could be a positive decimal value in between 0 and 1. Now, because A can't be equal to 0, we can sort of merge those two statements and say that the sequences of this linear type will have a limit as long as that A number is in between -1 and 1. So when you're looking at a recurrence relation, you will be able to tell if it's going to have a limit. So as we saw previously, there are graphs that can demonstrate this. So if it's divergent, so if your A number is greater than 1, it's getting bigger and bigger all the time. If your A number is less than -1, then your sequence is going down the way. Your convergence ones are the ones where you get this limit value. So what happens is your graph, right, will level out at a particular value and not go below that, right? So this one here, it would level off, and that's what happens on the calculator. So you don't need to memorize those graphs, those are just for information only. But this bit, next bit, we do need to know, how do we find this limit value without having to sit and press our calculator loads and loads of times? So for the recurrence relation, if we can see that a limit exists, right, that means that the terms in our sequence, and remember the notation that we use, so U1, U2, etc. Further on, we would talk about the nth term. The one before the nth term, we would use U subscript n-1, the one after the nth term, you'd call that un plus 1, the one after that un plus 2, and so on. So that's just terminology. That's just describing the sequence and the positions of the terms. So what happens when a limit exists is eventually all the values, initially your values are changing. So when you do a calculation, your u1, your u2 is different, your u3 is different, and so on. But eventually what happens is all these terms towards the end of the sequence, or if it keeps on going, they don't change. It settles at a particular value. Right, so what we're doing, what we say there is that as n tends to infinity, so the further into the sequence we go, the higher the value, then the more likely it is that these terms are going to become or settle at a particular value. We're going to call that L, which is our limit value. So what we mean by that is your sequence will start off with different numbers, u1, u2, u3, u4, you have numerical terms going on there, and eventually when you keep pressing your equals button, your calculator, there's it starts not changing, and that's your limit value that you've reached. Now, this is the method that we would go through. So we've already looked at this question, un plus 1 equals, or this recurrence relation, 0.2 un plus 4 u naught equal to 3, and we found that it did have a limit of 5, so I think it was it. So I already know that. So what we write down though, and this is the method I need you to get rid of, you need to say why a limit exists when you're looking at a recurrence relation. So you'd say since minus 1 less than 0.2, that's the value in front of un, less than 1, a limit exists. That's part of your working. That needs to be stated. So what we're saying is n tends to infinity, right? So you'd write that little symbol there, n, then the little arrow, and that's the infinity symbol. We say let the un term be equal to the next one after that, which is un plus 1, equal to L. That's you introducing the limit letter. So there's your recurrence relation. So you're replacing your un plus 1 and your un. They are getting replaced by that L value because they've become the same. So when you've done that, in that recurrence relation, you've then got an equation that's got the same letter, so you collect those terms on one side. So this is like 1 whole L take away 0.2 L. You can write that in a kind of factorised form, if you're wondering where that 0.8 comes from. Right, it's 1 times L and 0.2 times L, or take the L out as a common factor is another way of thinking about how we get that 0.8. Right, one take away 0.2 gives you 0.8 L. That gives you 4. You then have to divide by that 0.8, and I'm going to say to you, this quite often comes up numerically. So in the not numerically, in the non-calculator paper. So when that happens, you'd be expected to know how to divide by 0.8. So as we can't divide by a decimal, we change it into a whole number, and we do that by multiplying top and bottom by 10. You get the equivalent division, 40 divided by 8, and that gives you the limit value of 5 as we got before, and you find that on the calculator. Alternatively, there is a formula that you can use to work out the limit, which is this expression here, where it's the b value on the top over 1 minus whatever that a number is. That some people prefer to use that. I'm always going to stick with this one up here, because the problem is I've seen so many people who forget where the A and the B go and what the A and the B stand for, so they can't get it, and they get it round the wrong way. So if you just think about your recurrence relation and talk about a limit value replacing the un plus 1 and the un with L, then you're less likely to go wrong. So why are we doing this? The following type of question is one that illustrates what we do, or why we do the recurrence relation. So an industrial complex, they've asked for permission to dump 50 units of chemical waste into the sea. It's expected that the natural action of the sea will remove 40% of the waste per week, and they've been asked what the long-term effect of dumping that waste into the loch would be. So this is your steps how you would tackle a question like this. You would need to, it doesn't tell you in the question, you need to set up the recurrence relation. So you introduce your letter. Most of the time that's going to be the letter U. Subscript N, this case it's talking about weeks, so it's UN, the number of units of waste after N weeks. Now we know that 40% is being removed, right? So that 0.6, right? If you've got 100% minus 40%, that's where your 60% will be left, right? That's why 0.6 is your multiplier. So 0.6 times UN, and then it's dumping another 50%. So at the end of 1 week, you've got 60% from the previous week, plus you've got a new amount of 50. So once you've stated the recurrence relation, you go on to try and find the limit, but before you do that, you need to say a limit exists, and then you put in the little statement why it exists. So -1 less than 0.6 less than 1, and then to work out your limit, you set it up in the following way. You say as n tends to infinity, let un equal un plus 1 equal L. Take your recurrence relation and replace the un plus 1 and your un with that L value. And then it's a case of solve that, get the L terms together, so subtract the 0.6, so that's like 1 whole take away 0.6, which is 0.4. You need to divide by that again. You could get this in a non-calculator paper, so you would times by 10, which gives you that equivalent division. 500 divided by 4 is 125. So your conclusion, in the long term, the amount of waste residue in that loch would settle about 125 units, and that would be you'd need that conclusion. So there are 4 steps to these types of questions. Set up a recurrence relation, including the U0 value. So we noticed up here, can't remember if I mentioned that, but the U0 value was 0 unless it tells you otherwise. You assume there was none at the beginning. State why a limit exists. That's quite important that you put that in. That can often earn you a mark. Work out the limit by setting it up, introducing the letter L, and then replacing in the recurrence relation, and then doing the calculation. Now we could have done this numerically, however that can quite often mean lots and lots of calculations to get to the long-term situation, till you get to a point where actually it's levelled out on the calculator 125, and that's what I'm saying about pressing the calculator over and over again. So I've emphasised here the algebraic method that I've just shown you must be used if you're asked to work out long-term effects or long-term situations. And you'll see in the following example, like this sort of thing, the long-term effect is used in the question. So deer population estimated to go down, drop by 7.3 each year. They're also hoping to introduce another 20 deer into the forest. Your initial deer population is 200. You're asked how many will there be in the forest after 3 years, and then what is the long-term effect of the population. The long-term effect part, that means work out the limit algebraically. But the first bit, I mean, there's nowhere in this question that tell you to come up with a recurrence relation, but that's what the expectation is, and it's about recognising it's that type of question. So first thing you should do, set up the recurrence relation. Population is going down, so 100% minus 7.3% gets you to 92.7. You need to change that to your multiplier, and that should of course say divide by 100, right? And we get 0.927. So there's your recurrence relation. Un plus 1 equals 0.927 UN, and then that plus 20 is the amount that's been added in every year. There's the U0, so that's you set up the recurrence relation. You then need to work out for the 3 years. Now that does mean showing you're working, and laying it out in that way. Remember, it's about using the previous term to get the next term and so on. And notice we do get lots of decimals here, but in the context of this question, you need a conclusion and a little set. That means full sentence. After 3 years, there will be 215 deer in the forest. So, not in the next part, we were asked about the long-term effect, and this is where you go on and say the bit about the limit. So a limit exists because -1 less than 0.6 less than 1. As n tends to infinity, you'd say un plus 1 and un are equal to that L value. You replace in the recurrence relation with the L. Tidy up your L terms on one side. So we're doing 1 take away 0.927. Right, this time you'd have 0.073 when you divide at the bottom there. Numerically, that wouldn't be a non-calculator question, and this would be in a calculator paper. So it comes out as 273.9726. And normal rules around, and you'd say, oh, that would become 274, but actually, because this is a limit value, it won't ever reach the 274, and because in the context of the question, it's talking about deer, so you round down the way, which is not normal rounding, but what we'd say is in the long term, the population of the deer will settle around 273, and it's important that you use the language settle around 273. So last question. This one's a wee bit different. Right, a sequence is defined by this recurrence relation here. So there's some missing coefficient terms in it, and you're asked to work out, given that they tell you the limit and they're asking you to work out the value of that k number. So because we know the limit value is 27, remember what that means. It means our un and un plus 1 terms are going to be equal to that limit value, which is the 27. So it means in your sequence that you've got, you can replace the un plus 1 with 27, and you can replace the un with 27 as well. Right, so these are the terms that are become our limit. So they're getting replaced with a 27. So that gives you a little equation with k in it, and we basically go on and solve it for k at the bottom, and you get a numerical value. So that just demonstrates that slightly different type of question. You can come across either or be examined on either of those types of terms. Certainly the first type that we did with the deer and the forest problem is more common than this one here, but it doesn't mean you won't come across this type where they tell you the limit and you have to work out some missing coefficients.